Hello guys and welcome to another lecture video for ME260. So for this video and the succeeding videos, I will be discussing a variety of concepts and examples for velocity analysis. So to get started, we have the outline here. We will study the prerequisites or a review of vectors, and then we will go into position analysis, which is basically just finding the relative position of our linkage in terms of the angles. And then we have the velocity analysis, which is how do we find the velocity and relative velocities of our mechanism, no, to be specific, our forward mechanism. So our analysis here, instead of the graphical method, we will discuss the analytical method or the exact method. No? Analytical method, slightly numerical since the equations are not that easy to solve analytically. So, I'll get into that later. So let's have a review regarding vectors now before we delve into a lot of these concepts. So vectors help us predict the positions and represent the positions of a variety of physical phenomena, including their velocity. So we can use this for position, velocity, and also acceleration, and a lot of things. So we know that if we have a vector A, notated by this A arrowhead, it usually has its rectangular components or its base components, no? Which are just its sum, no? Which are AX and AY. So we know this rule is called also the triangle law, no? So it doesn't have to be I mean, it doesn't have to be exactly right triangle to make a sum, no? So basically if you have two, no, so this AX and AY, for example, is slightly oblique. If you have these two vectors, if you add these two vectors, what happens is the sum of these two vectors will be the point of its tail to the point of its head. No? So that is basically the triangle law as well. Okay, so an easier way to represent vectors, a more compact version, no? So mas maikli, no? It might be too much, but it is actually a better way or much simpler way to represent vectors. Since if we're dealing with two dimensions, no, we can represent this into or using complex numbers. So you have the x-axis, no, as the real axis, the horizontal axis, and then the vertical axis or the imaginary axis, no, to represent your vertical position. So alternatively, we can also use different systems for complex number instead of the rectangular form or the Cartesian form. We can also use the polar. No? So instead of a plus bi, if you can remember, you can use our angle theta. No? So we have this representation. If you have, let's say, a complex number z, no? Usually this is notated as z, we can equate this as the the modulus, no? Or the radius or the modulus, and then e raised to j theta. No? We will usually notate this instead of I, no? Some textbooks use I, but I will use j here for the imaginary number. No? Okay. So you have r e j theta. But in other words, this is also the same thing as saying it is a vector, no? Because as you can see here, you have r here as your vector, for example, and the sum of these two vectors are this rectangular components which are a and b. So as you can see, a here is r cos theta since this is the adjacent side, and then we have r sine theta in this opposite side since it is in the opposite, no? So we have a j here because in the coordinate system for complex numbers, which is also called the Argand diagram, you have x, no? So the real number line, no, the real axis here, you have negative infinity to positive infinity. For the imaginary axis, you have positive I upward and a negative I downward. No? So it could be positive 2i, positive 3i, positive 4.5i, square root of 5i, and so on. So we extended the real number, or we basically have a much larger representation of the number system in two dimensions. So in Cartesian form, you can use either this. Sorry, in a complex number, you can either use a polar form, or actually this is also called the exponential form. As long as you have an angle and an r, no, it is synonymous still to a polar form. And then you have the Cartesian form, which is it is additive, no? So you have these rectangular components, which is this is just a, r cos theta is a, and then r sine theta is b. Okay, so take note here that we will use a convention for theta, that theta is always measured at the positive x-axis, no, from the positive x-axis. So if it is counterclockwise, it will be positive, no. So in this case, it will be counterclockwise, no. If it is on in the bottom, no, if r is in the bottom here, it will be clockwise, so the angle will be negative. Okay. So let's get into action, no. Since we are dealing with the positions, or before we actually dive into the velocity, we want to first understand the position analysis. So for the position analysis, this is the same as displacement analysis basically, but we will focus more on the exact values, no? A more compact version of solving for the relative angles, no, of your four bar mechanism. So as you can remember, you have as if you have a four bar mechanism, just remove this AD link here and the CD link here. Then you have this AB and BC links, no? As you can remember. And if we're talking about vectors, no, in the context of vectors, if we add these two vectors here, AB and BC, then you have this sum, no? So same goes for if we add here now the AD and the CD vectors, then it is also the sum, no? This orange, no, orange vector, you can imagine this is an orange vector. This is still a sum of AD plus CD. So instead of calling this AD and CD, AB and BC, I'll just call this R1, R2, R3, and 4, saying that this is the first link, no? We have link 1, link 2, link 3, link 4, no? So therefore, if we find if we do the equation, no, for vectors, since we know that the sum of R2 and R3 is this orange, and the sum of R1 and R4 is also this orange, we can equate these two, no? So we have R2 plus R3 is equal to R1 plus R4. Now, in other words, we can also simplify this. We can transpose this R1 and R4 to the left side. And we have R2 plus R3 minus R1 minus R4. Okay? So, adding another convention or another variable or parameter, we also have theta. No? The angles, the relative angles. So, we have the lengths. We also have the angles to represent the position of, let's say, B. No, where is B now? No? If you rotate this A, where is B? So we can know if where is B if we know theta 2. No, or at least you know the one angle here and every side. No, we can know the position of B. Okay, so we have here theta 2, theta 3, theta 4. So theta 2 basically is just linked with the R2, no, the second link. So in theta 2, we use theta 2 here because we are referencing this rotation of link 2. Same goes for theta 3, we're referencing the rotation of R3. And theta 4 is when we are referencing the rotation of R4. Ano? So we will make use of this rotation for all of this, for the subsequent, no, examples. No? So another thing to remember, these angles here, no? So actually, we still have theta 1, no? So since R1 is not moving, so theta 1 is just, well, if you have an angle here that is referencing this to the positive x-axis, no? So tandaan nyo, we are always referencing with the positive x-axis. So this R1 here, this link here is 0, no? Because it is, sorry, it should be here, no? So it doesn't have an angle. So it is zero, no? It is on the x-axis or the positive x-axis. So theta 2 has an angle here that is about greater, maybe 100 or 120 degrees, no, for this example. And I think that's it, no? So we are always referencing from the positive x-axis, as you can see here, no? And then counterclockwise to make things positive. Okay? So we will only analyze, so it is actually hard to solve for the exact, no, velocities, no, or positions, as you can see in the previous in the previous topic. No, it is actually quite challenging to solve it. And we actually have a more compact way to solve this, no? But we only have two, or we will only discuss two four-bar mechanisms that we can solve exactly, no, or analytically, which are just the standard four-bar mechanism, and then the second is the slider crank. Okay, so we will now make use, no? We will now make use of this concept in complex numbers and vectors to to understand or to derive for the relationship of this these angles right here. Now, so we know that again, no, this vectors are the sum of this or that their sum should be zero, and we know that in the complex number we can use this notation, no, to treat their vectors. Then what we can say here is referencing everything here. So you have R2, no? So we have R2 plus R3, R1, R4. So these are vectors. So take note that these are vectors. So gawin na lang natin is instead of R vector, we will just rotate this into this form. So you have R2 E R2 R2 EJ theta 2, okay, plus R3 EJ theta 3, okay, minus R1 EJ theta 1 minus R4 EJ theta 4 is equal to 0. Okay, so we already have an equation, no? So we can relate the relative values or the relative, yes, the relativity of these angles here. So let's say we know theta 2 and theta 4, no? We can solve for theta 3, for example. And also, of course, their lengths. No? So the lengths here or also the radiuses are r. No? And then we have the angles 2, 3, and 4. No? So now it is quite hard to really use this. No? We cannot really use this in this form. So we can convert this into its Cartesian form. So if we convert this into its Cartesian form, Cartesian, we can say here that you have R2, you have we know that e raised to j theta is equal to actually you have r here is r cos theta plus j r sine theta, no? So in your advanced math probably or in advanced algebra, no? So you have here r2 cosine theta 2 plus j, or actually I'll just include everything here, I think. No? I think I'll just factor out the r, no? I can just factor out the r. So j sine theta 2, okay, for this one. And then we will do for the other terms. Wait, yeah. Cosine. Okay, minus, you have r1. So we know that theta 1, no, we've already reconciled that theta 1 is equal to 0, sorry, 0. So we can make use of this to simplify cosine 0 and sine 0, no? So R1 cosine 0, no, 0 degrees, plus J sine 0, no, for 1. Okay, and then minus R, should I just write this here? So last one, cosine theta 4. So they are unknowns, no? J sine, it's not going to fit. Make it fit, no? R4 cos theta 4 plus J sine theta 4. And then equals to 0, no? So as you can see, we can cancel this. So cosine 0 is equal to 1, sine 0 is equal to 0. So we only have R1 left here. So R1, so j times 0, 0. So R1 times 1 only. And then, so we can have here, we can also segregate the real and the imaginary part, no? So, this is actually a technique, no? You might not realize this, but this is a technique in partial fractions where we can equate the coefficients, no? Equating coefficients, right? So if you equate this into the right hand side, so basically you have 0 plus 0 I here on the other side since this is 0. So we can equate this plus 0 plus 0 I, no, on the right hand side. So I will not write the 0 plus 0 I. So for the real part, so everything that doesn't have a j, so you have R2 cos theta 2, right? Plus R3 cos theta 3, and then minus R1, and then minus R4 cos theta 4 is equal to 0. And then for your imaginary, okay, okay, for your imaginary, you have R1, sorry, imaginary here is R2 still, R2 sine theta 2. We can write the J, no? We can write the J. We can write the J here. Although, sige, I'll write this down for now. And then plus J R3 sine theta 3 minus, so we don't have an imaginary part for R1, no? So since this is 0, so we only have R4. So J R4 and then sine theta 4 and then equals 0. So basically, if you can imagine, you can just factor out the j, no? So we can just remove the j here or factor out the j and then divide this by j. You can factor out or we can remove the j. So removing this j here, we have this real and imaginary portions, no? Okay, so now we have this two. What now, no? So why did we do this? So we want to find the relationship between these angles and this lengths here. So these are the lengths, no, or the radiuses. So let's say you have you have a given length here, no, or the lengths are given, and you also have theta 2 given. You can actually find theta 3 or theta 4. Okay, so it will make things much more easier, no, for displacement analysis, no. So moving on, we have this real and imaginary part. All right. So what we can do here, how can we solve for theta 3 and theta 4? There is a trick to do this. So one way to do this is to sorry is to segregate. No? We can segregate the R2 to the right hand side, left hand side, and then we segregate everything to the right hand side. So we'll just have R2 cos theta on the left and R2 sin theta 2 on the left. So let me show you what I mean here. So R2 cos theta 2 is equal to, so we have I'll just write here R4 cos theta 4 plus R1 minus R3 cos theta 3, right? And then you have R2 for this one. For imaginary part, you have R2 sine theta 2 and then equals to R4 sine theta 4 and then minus R3 sine theta 3. Okay, that's it, no? And then what I'm going to do here is actually I can square this both sides, right? I can square this both sides and then I could add these two equations. So after I added these two equations, as you can see, you have here R2 squared cosine squared theta 2, right? For the first equation plus R2 squared sine theta 2 and then squared here. Okay? And then you have here R4 cosine theta 4 plus R1 minus R3 cosine theta 3 and then squared and then plus you have R4 sine theta 4 minus R3 sine theta 3 and then squared as well, no? So what's the trick here, no? So the trick here is we could actually I think I did something wrong here, no? We cannot solve for ano. Oh, I'll just swap things here, no? So I'll just swap things here on the run because we're trying to solve for theta 3 and theta 4 nga pala, no? So we want to cancel one of this. So sorry, no? So just swap this to R3. Okay, and then this should be I'll just swap this to R2 and cos theta 2, 2, and 2, no? So you'll find out the reason why. 3, just swap things here. Okay, so why did I do that, no? Why did I do that? So the reason for that is because we want to cancel out theta 3, no? So as you can see here, we can factor out, no? So as you can see here, we are looking only on the left hand side. This is also the same as R3 squared multiplied by cosine squared theta 3 plus sine squared theta 3, no? So as you can see, we can cancel out this one. So this is equal to 1, no? So basically, we have R3 squared is equal to R4 cos theta 4, no? Minus R1 minus R2. Sorry, it should be plus, no? Plus, and then minus R2 cosine theta 2 squared. And then you have, sorry, plus, no? This is still on the right-hand side, no? Plus, it won't, no, because it won't fit, no? Kaya dito natin susulat. Minus R2 sine theta 2 squared. So this will be your relationship, no? So given the sides are given, for example, so all the r's are given, and one angle at least, no, which is, let's say, theta 2 is given. So theta 2 is given. We can solve for theta 4. So this is an implicit representation or a solution to the same uh, um, sorry, what did I say? So this is a representation of their angles, no? Kumbaga, kung meron kayong given na angle, theta 2, you can solve for theta 4. Ayan. Okay, mali pala yata yung na-solve ko. Tama ba? Tama naman, no? Okay, so tama naman na-solve ko, no? So you can solve for theta 4, okay, given theta 2 and all the lengths. So ito lang yung naka-type na version, no? So we can also solve for theta 3. So instead naman na nandito sa left-hand side yung R3 cos theta 3 and R3 sin theta 3, pwede nyong gawin naman yung nasa left-hand side naman tong dalawa, no? So para makancel naman tong dalawa, you can solve for theta 3, no? Given yung theta 2. Okay? So we can also do that and you can solve this at the same time. Sorry, ito pala yung theta 4. It should be for theta 3, no? Anyways. Sige. So, yung solution natin for solving, let's say, theta 3. So, again, imagine, no? The lengths are given. So, these are the lengths, no? All the lengths are given. You want to solve for theta 3, no? So, theta 3 is unknown. Given naman yung theta 2, no? So, you can solve using this equation. Ang problema lang, naka-implicit form itong ano natin, no? Naka-implicit form. Ibig sabihin, kailangan natin siyang gamitan ng numerical method, no? Actually, merong explicit way to solve this. Kaso nga lang, well, the problem is, it's quite long, no? You have to use a lot of extra steps, no? From the textbook. But we won't be too interested in solving this 100% exactly. Since we already have a calculator, we can just solve this implicitly, no? Or in other words, shift solve, no? So that will be the same for theta 4, no? So given theta 2, you can solve for theta 4 as well. Okay, so that's it for position analysis for 4-bar mechanism. Now we can also solve this slider crank mechanism with the same concept, no? So I won't do everything here, pero we can also do this as an exercise. You can try solving for theta 3, no? And B. So if you try to solve for theta 3 here, since theta 4 here is already 90, no? You should na 100% this is already 90 since this is perpendicular, no? So we don't need to solve for theta 4, we only need to solve for theta 3. And also, not just that, no. So we also want to solve for this to call this displacement or distance, no, not really the displacement, but the distance from A to C, no, horizontal distance. So this distance here is also varying, no, theta 3 is also varying here. Everything is varying the angle and this D. So E is constant, as you can see, it will never change. The lengths will never change, no. So the things that will change here are theta 2, theta 3, and D. Okay, so we can solve for theta 3, for example, given theta 2 and the offset and also the length of this slider crank. Okay, so I think that's it. You can also solve for the distance using this formula. Okay, so thank you guys and see you on the next video.